to Professor Farr for the invitation. Today, I'm going to explain one subject in Langland's program, and I feel that this time is a very good time to give a talk on my recent work, because last week Langland's received the Abel Prize that I'm doing, and 2 weeks ago, the Seok Shin, Professor Shin, came to here and gave a colloquium talk about Langland's program. So I feel that my subject is not too difficult, and hope that because my subject is the classification, and it has some technical part, and I hope that I hope that it is accessible to many of the audience here. Okay, let me start. So the title is the classification of discrete series. Let me write down. Of discrete series representations. And in this talk, I'm going to use this abbreviation. There are many the representations, but I'm going to use this abbreviation. For example, for superhospital and discrete series, I'm going to use SC or DS. Or for strongly positive discrete series, I'm going to use SPDS to save the time. And yeah, so going back to the title, so I'm going to talk about the classification of DS, discrete series representations of all GSpin groups. And this is joint work with Ivan Matish, who is in Croatia, University of Osijek. In this talk, I'm going to first start with the introduction. In the introduction, I'm going to start from the beginning. The first subject is just representation theory. And then I'm going to briefly explain the local Langlands correspondence, LLC. This is one big conjecture in Langland's program. And then I'm going to talk about today's talk, the main subject, the classification of discrete series representations. So classification. And there are two steps in the classification of discrete series. The first step is that I'm going to mention soon is the classification in terms of superhospital. And its classification, it is not just classification of discrete series, and it is classification of special kind of discrete series, which is strongly positive discrete series representations. If you remember the talk 2 years ago that I gave when I came to here, I mentioned a little bit about the classification of strongly positive discrete series representations. Maybe because I don't have enough time, I might just focus on the second step. The second step is from, as you can guess from the first step, from strongly positive discrete series representations to discrete series representations. To get the result on the classification, the main tool is the following. The main tool is so-called Tadish's structure formula. Okay, so Tadish is a mathematician in Croatia, and Ivan Matish is also from Croatia. He is a mathematical grandfather of Ivan Matish. Anyhow, so this is one main tool, and if I still have time, I'm going to explain the application. Why this is the one important subject in Langland's program. This is somewhat related to the main conjectures in Langland's program. For example, local Langland's correspondence. Okay. So let me start with the the basic setting, the basic the mathematics, which is representation theory, the 1, and A, the representation, as all of the audience know, let me write down the representations definition. Representation pi of a group H on a vector space is a group homomorphism pi from the group H that we want to study to GLV. Okay, and we among representations we are also want to use the definition of the irreducible representations. So let me just write down the definition of this one as well. The irreducible representations means of H is a non-zero representations, non-zero representations that has no proper sub-representations. Representation pi and W, where W, of course, is a subspace of V closed under the action of these representations, under the action of pi G. Okay, so this is very basic the representation theory, and there is a certain reason why I write down the definition of the irreducible representations, even if all undergraduate students know the definition of this one, because I'm going to tell about this later, but to study the Langlands program, the one side is certain representations, and to study representations, the important things that we need to know is whether that representation is irreducible or not. That's the one main theme in the Langlands program. Okay, before you start the local Langlands correspondence, let me just ask a question. This is just very general definition of the representations. So you can ask this kind of question. So what kind of representations do we study in Langlands program? There are, I will say that there are three, I will mention three representations. The first one is called admissible representations. The second one is automorphic representations of certain group. And also, the other side, we have Galois representations. Okay. So when you mention the representations, we need to mention about the group as well. So this is admissible and automorphic representations of so-called connected reductive group over local field of characters 0 or characters P or global field. Okay, I'm not going to explain the definition of these the representations. Rather, I'm going to give you some examples of this. For example, the connected reductive group, the most important example is the GLN. And also another example, other than GLN, is the classical groups. And another group is the GSpin group that appears in the title, GSpin. And the remaining thing is the exceptional groups. So basically, in the Langlands program, we study like a certain admissible representations of GLN were classical groups, were GSpin, were exceptional groups. In the relation with the Galois representations. That's the local long lengths. And for automorphic representations of GLN and classical groups, and those groups defined over a global field, we want to find the relation with also Galois representations. That's the global long lengths. And today, I'm going to focus on only the local representations, meaning that I'm going to study the automissable representations. Okay. And to study this kind of representations, for example, automissable representations, we also study, we also use this representation called induced representations. This is kind of functor, so it is induced representations, kind of functor from representations of certain subgroup to representations of the original group G that you want to study. For example, GLN or classical groups or GSpin groups. And this group is so-called Levy subgroup. So if it is functor from representations of this Levy subgroup M to representation of G, then we sometimes use this notation G and M, or instead of M, we sometimes use the so-called parabolic subgroup that contains M. For example, because most important example in the long length program is GLN, let me talk about the GLN case. So G is GLN, this is M by M matrix. The Levy subgroup is of the form like so this certain subgroup of GLN, and there are a bunch of GLN here. GLN1, GLN2, and GLNK. So we usually use this notation like GLN1 times and GLNK. So the representations of M means we have bunch of, because we have a bunch of GLN, so we use this bunch of GLN like sigma 1 and sigma 2 and sigma k. And if you use the induced representations, if you apply the induced functor, it becomes induced from this one. So we have tensor product here. And this becomes representations of the original group GLN. Okay. And then I can mention about the local long lengths before we go into detail about induced representations. So the B was the local long length correspondence, so which is one main conjecture in long length program, is that the long length found certain relation between two different areas which seem to be unrelated before long length thought about it. So the one side is the analytic side, and the other side is number theory side. And the object in this the side is called in this side is called so-called Galois representations that I wrote here in the answer. Galois third one. That's the object in the number theory side. And the analytic side, the object is so-called the automissable representations and automorphic representations. But here, because we are going to consider only the local long length correspondence, the object in the analytic side is so-called automissable representations of the connected reductive group over a local field F. We usually consider the character 0 case. Well, also local long length says there exists finite one map from analytic side to the number theory side. But this is not this is somewhat vague correspondence between these two. So to strengthen the relation between these two sides, we use so-called L functions. So L functions defined here is so-called alternate functions. And the L functions, we can define, you can use several methods to define L functions. And the L function that I use is so-called L functions from Langlands Shahidi method. So the basic question in the local Langlands correspondence is whether those two L functions are equal or not. Okay. To strengthen the relation between these two sides, the correspondence. Okay. And before we go into the main subject, the classification of discrete series representations, let me explain a little bit about the Langlands program. This is kind of like a continuation of Sogushin's talk. Langlands, when he defined what he did long time ago, this idea is from the letter to Vail. What Langlands did at the time when he was like 30 years old, 1966, he generalize and study so-called Eisenstein series. Eisenstein series. To any connected reductive groups, and he studies the properties of the Eisenstein series. For example, the example would be the functional equation. And another thing is analytic continuation. And by looking at some constant term of the Eisenstein series, because Eisenstein series is kind of certain the series, infinite series, because this series has this function is a periodic function. It has a Fourier coefficient, so we can calculate like constant term and non-constant term of the Fourier the Eisenstein series. And Langlands studied like a constant term, constant term of Eisenstein series. And also, if it is available, then he used a so-called the theory of intertwining operators. He defined new L functions here. Okay. And in the constant term of Eisenstein series, the new L functions appeared, so that using the properties of the Eisenstein series, we can prove also the same properties, functional equation and analytic continuation of these new L functions. So that this L function satisfies nice properties like functional equation and analytic continuation. In the case when the representation is genetic, and there are certain properties that this Eisenstein series satisfies, so that we can define the L function nicely, that's called L functions from Langlands-Shahidi method. So L function from Langlands-Shahidi method, using the properties of Eisenstein series, we can prove, for example, like functional equations and analytic continuation and etc. So that's how they prove the properties of the L functions from Langlands-Shahidi method. Okay, and also very briefly, this is very to give you the example. In the classical case, the Eisenstein series looks like this. G and S is given by sum of over C and D is in G square, and GCD and C and D is equal to 1, and sum y to the S over CG plus D to the 2S. where here is a G is a complex number, x plus iy. This is the definition of the classical Eisenstein series. And we can also calculate the constant term of this Eisenstein series, because this one is also a periodic function, namely like E of z plus 1 and s is equal to E z and s. So it's a periodic function. So by using the Fourier analysis, it has a Fourier coefficient, so that we have like, we can write down this one as like some n is in z and some coefficient, Fourier coefficient y and s, and e to the 2 pi I n x. Okay. And if you calculate the constant term of this Eisenstein series, which meaning that if you calculate A0ys, it becomes like A0 and y and s becomes integration from 0 to 1 of this Eisenstein series, x plus iy and s and dx. And this becomes, after you calculate this one, it becomes y to the s plus and L 2s minus 1 over L 2s times y to the 1 minus s, where L function here is the complete Riemann-Zeta functions, which is defined by pi to the s over 2, negative s over 2, and gamma function s over 2 times Riemann-Zeta functions. So which is given by this one. This is so-called complete the Riemann-Zeta functions. Other than Riemann-Zeta function, we add this part, the real part of the L functions. And as you can see, the constant term of the Eisenstein series, the L functions appear here. And we know that in the classical case, Eisenstein series satisfies a certain functional equation, which meaning that EGS and EZ and 1 minus s has certain relation that will give you the functional equation of the complete Riemann-Zeta functions. Also, analytic continuation, we also know that this one satisfies analytic continuation. That will give you also analytic continuation of the this complete the Riemann-Zeta functions. So what Langlands did is generalize this one to any connected reductive groups. So we can consider this one as a series of like a SL to Z quotient by some Borel subgroup, and then generalize that group to any connected reductive groups, and also calculate the constant term. And sometimes, for example, when pi is genetic, we can somehow define the L functions, and the L function that appear here that satisfy this functional equation and analytic equation, because the original Eisenstein series satisfy this functional equation and analytic continuation, exactly like the classical case. So the Langlands work, original work, is to prove the properties of the Eisenstein series, the generalized Eisenstein series, which are the functional equation and analytic continuation, and apply those properties to the new L functions. Okay. So this is the introduction, the Langlands program. So going back to our subject, so the subject is a classification of discrete series. So I'm going to explain where this subject appear in the Langlands program. Okay, let me erase.
So if you take some generalized Eisenstein series,
yes, generalized, yes, yeah.
And you look at the constant term,
yes.
then you get some different L functions appearing, or
yeah, different L function, that the new L functions that Langlands defined. Langlands defined the new L functions by calculating the constant term of the generalized Eisenstein series. And what Scheide did is that in the genetic case, there's the certain way to calculate the constant term of the Eisenstein series. using so-called the theory of intertwining operators, so that he can define also the L functions using the Eisenstein series and the theory of intertwining operators. And then by calculating the constant term, that L function appear like this. That means that will give you the relation between the properties of the L functions and the properties of the Eisenstein series.
So, for example, in this setup, how can you read Ls out of A0 Ys?
Can you say that again?
Can you compute this L function in terms of the constant term directly?
Can you compute the L function directly from here? Yes.
There is some formula one can.
Yeah. So because we know that the Riemann-Zeta function is sum of 1 over n to the s. Then if you integrate this one from 0 to 1 with respect to x, you can find certain the sum of the Riemann-Zeta function appear there if you integrate this one directly. Maybe it will take a little time to show that the calculation. Let me try that after the talk. Yeah, integration of this one from 0 to 1 of this one. Okay, and yeah, because this is also sum, you can. I think I haven't. I don't see right now, but if you calculate this guy by using the sum, you can easily see that this sum 1 over ns appear there after you integrate. Okay. Any other question? Okay. So to continue, So to study local Langlands correspondence, the object in the analysis side is so-called admissible representations. So there's a nice filtration of admissible representations. Of admissible. The most simple case is superhospital that I wrote over there, the red one. The superhospital to discrete series and also so-called tempered representations. And finally, the last the class is admissible representations. This can be defined by in terms of the metric coefficient, the growth properties of the metric coefficient that I'm not going to write down. And also there's another class between superhospital and discrete series. This is so-called the strongly positive discrete series representations. Okay, and the main problem in the classification of discrete series is the following. In this filtration, is the following. Is that problems in this filtration is the description of each class, like discrete series or tempered, in terms of the previous class is previous class. Okay. For example, how? For example, if you want to classify the tempered representations, so say we have tempered. This is tempered. We want to classify this one by embedding this one into certain induced representations that I introduced before, which in this data is a representations of so-called Leib subgroup, where the representations of Leib subgroup is discrete series representations. Okay. And also to classify the second class, the discrete series, in terms of superhospital, that means by considering discretes and embed these representations into certain induced representations, where inducing data usually it is supercuspidal representations. So in each step has a certain has a name. So for example, from discrete 3 to tempered, this one has a name so-called R groups. And from supercuspidal to discrete 3s, meaning that we want to classify the discrete 3s in terms of supercuspidal. This is called classification of discrete 3s representation, which is the title. Okay, so I'm going to focus only this part. This is totally different the project, the R groups. Okay, so the basic question that we can ask here is that is induced representations that I mentioned irreducible? That's the main questions in this subject, the classification of discrete 3s. Well, sometimes no, even if sigma is irreducible. Even if the representations of left subgroup is irreducible, sometimes induced representations of that left subgroup might be reducible. Okay? So we need to be a little bit careful. And question 2 is that, okay, so what if this representation is reducible? Then we need to study so-called subquotient, or sometimes just quotient, or sometimes sub-representations of this representation space. Okay. So this vector space, it has certain sub-representations, and of course subquotient, and sometimes it has the quotient. And how? How do we study this subquotient of these induced representations? It is by using so-called the Jacob functor. Jacob functor is also the functor from representations, but from representations of the original group G, the other way around, to representations of the left subgroup. Okay. And the studying the Jacob functor is so-called Tardis structure formula that I mentioned in the beginning. Okay, which is the main tool in the classification of discrete 3 representations.
Sorry, so you're assuming that sigma is the discrete series representation now, right?
Sometimes when sigma is supercuspidal, we also consider when sigma is supercuspidal. Yes, yeah. When original representation is discrete 3, yes, and then we want to embed that one into certain induced representations where inducing data is supercuspidal representations, and some part that I'm going to explain soon is that some part of GL part is representations of discrete 3 representations. And yeah, at least one part of the inducing data representations of left subgroup should be the supercuspidal representations. And the previous class, using the previous class, you want to explain, you want to classify the second class discrete 3 representations. Okay. So from now on, I'm going to just explain the result on the classification of discrete 3s. In the most important example, this is second. The most important example is, of course, GLN. In this case, it is constructed by Bernstein and Jelabensky in 1980s. He says integrable, which is another name of discrete series, the same as this one. Discrete series representations, rho, and I'm going to write down ds here, meaning that this is discrete series, of GLN. So this is irreducible representations of GLN. And I'm going to, they classify the more general, the representations, the more than the square integrable, so-called, essentially, square integrable representations. Here, this contains a little bit technical part. So let me just briefly write down the meaning of essentially. That means we allow twisting by certain character of determinant. And I'm going to use this notation nu. This will tell you the unitaricity of the square integral representations. That means if we don't have like any twisting, these square integrable representations, by definition, it is also unitary representations, unitarizable representations. And this is classified by Boltzmann-Jansky. This is classified so-called the segment. So there are a bunch of representations, but here, as I explained in the beginning, the classification of discrete series is classified by the first class, which is superclassifiable representations. So there are a bunch of the superclassifiable representations here. So we have rho SC, so SC means superclassifiable, and a bunch of rho SC, the same one. And also here we twist by certain this determinant, the character, to the certain power. A, and second one is we add one more here, rho SC, and all the way up to nu to the so to another half integer, a plus n. Okay, and you might ask how here, and this is exactly given by this description, namely, if you have like a rho ds, essentially square integral representations. We consider this one as the unique, irreducible sub representations of certain induced representations using this bunch of superclassifiable representations, which is given by due to the starting from this part a plus n rho SC and until the first one due to the A and rho SC. So as I mentioned, these induced representations might be reducible, but it is known that this induced representations of GLN has the unique irreducible sub-representations. That means among the sub-quotient, there are only one sub-representation. Others are all other sub-quotient are quotient, not sub-representations. Okay, so we can classify. So we can classify these the essentially square integral representations using this data, the superclassifiable certain superclassifiable representations of GLN, and also twist by from a plus n to a using this data. So here we use this notation. This just notation using this data. So we just write out like this guy, delta starting from a rho SC and due to the a plus n rho SC. This is just notation, meaning that the unique irreducible sub-representations of these induced representations. Okay. So in the case of GLN, it is fully classified by, yes?
So in this matter of twisting, I'm confusing you are working over the field of characteristic 0?
Yes, case of zero case, yes.
Yes, then it's okay.
Also, we can also consider this one as a case as P case. Do we have some problem?
If the character is P, then the segment appears in the same way?
I have to check, but if I remember right, this result is true for any characteristic.
Right?
Character 0 and character p case as well.
Oh, that's what the Bernstein-Jelinek result.
Yeah, that's Bernstein-Jelinek result.
There's no restrictions.
Yeah, if I remember right, there's no restriction. Right. Yes, yeah, because also my result is also depends on the characteristic case, but only due to the L functions from Lagrange-Hyde method, the properties. When we use a property L function from Lagrange-Hyde method, we need a condition on the characteristic. Other than that, other technique applies for any characteristic. So this is also true. But I have to check, but I think this is true for any characteristic. Character 0 case for sure. Character p case as well.
When I attended the short-case lectures of these topics, I remember if we had something characteristic P, then the segment might be different. I remember. Well, anyway,
I will also check, yeah. But in the case of classical groups, it depends on the characteristic case, yeah. But GLN, I will check as well. But character 0 case, no problem. Okay. So the second example, before we get to the all GSpin groups, is the following. Example 2 is the case of classical groups, meaning that, like, for example, the example of classical group is special orthogonal groups, odd case and even case as well, and SP2N, and unitary groups as well. This is a result of Moglan and also Moglan and Tadish. Okay, and I'm not going to write down the structure of this one because it's a little bit complicated. I'm going to just mention the two main tools in the proof of the case of classical groups. The first one, we need two main tools. The first one is the theory of intertwining operators. I will briefly explain what it means. It is just like a map between certain induced representations determine the certain one element of Y group element. For example, like sometimes the representation GL part, they switch when you apply the Y group element. And there's a certain map from certain induced representations to another the induced representation after you act by the Y group element. And this will tell you, this will determine also the reducibility of certain another representations. This is one main argument when Moglan got a certain result on the classification of discrete series of the classical groups. The another one that I wrote down already twice is Tadish structure formula. Let me write down just Tadish structure formula. Like so, because I already wrote down twice. And let me skip the example of Tadish structure formula because I only have 15 minutes. What time do I have? Until 5:30? Okay. Let me skip that the technical part. And let me just write down our project and where we stand. I'll just briefly mention the recent result. So our project is that we want to generalize Moglan and Tadish this result, this classification of discrete series of classical groups, to other reductive groups. But I hope that I want to generalize to all other groups, but not all. To some other reductive groups. And currently, we are working on the all GSpin groups and also general unitary groups. And this is let me just tell you a little bit about this approach. This is a little bit different from this approach, the approach of the Moglan and Tadish. So I would say this is just new approach, meaning that we focus more on Tadish. Because this is joint work with his grandson, mathematical grandson. Anyhow, so we focus more on Tadish structure formula, and it has a certain merit. It could be potentially applied to other connected reductive groups, especially the simulated reductive groups that we are working on now, other than the all GSpin groups. For example, like the GSP or GSO, those kind of groups. Let me summarize what I have explained in the recent result. So we have the classification of the strongly positive discrete series representations. We also classify the discrete series representations of certain groups. And the result of this one is that in the case of GLN, they just do it directly for any discrete series. This is by Bernstein and Jelevinsky. And classical group, this is by Moglan and Tadish. And all GSpin groups. From this part, we split this subject into two parts. The classification of strongly positive discretes, I recently classify that one. Also even case as well. And recently, which is this title, the classification of full discrete series, we construct this result. We obtain this result. So this is Moglan and Tadish. Myself and Matish. And also we are working on the simulated unitary groups, simulated the classical groups. In the case of strongly positive discrete series, it is slight generalization of this one. So we don't have much difficulty in this case. But in this case, we are working on this one, but we found the one important case which cannot be dealt with our previous idea. So we need the new approach to attack the case, the full classification of discrete series of the general unitary groups. Okay, let me mention a little bit about this part, why we split these two cases. In this case, after Moglan and Tadish classified the classical group case, the Matish classified by using the different approach. He classified the strongly positive discrete series of the metaplectic group. And I was able to apply those cases to all GSpin groups. And together, by generalizing his idea, and we were able to attack the full discrete series representations. So the reason why we split this case starts from his idea, the Ivan Matish idea, original his previous result on the classification of strongly positive discrete series of the metaplectic group, the other groups. Okay. Any questions so far? Oh, okay. So can I?
You still have 10 more.
Okay. Okay then. Okay then. Let me explain a little bit about main result. without writing down the complicated part. Now I think I can erase this part as well. Okay, so let me write down some tower, which is this is the classification of the discretes. This is main result. The basic setting is that F is a non-Archimedean local field of characteristic 0. We need this condition because we also sometimes use the theory of intertwining operators a little bit. If we can generalize that lemma to any characteristic, we can also generalize our result to any characteristic case. And Gn is all GSpin groups, 2n plus 1, defined over this local field F. That means, well, there are several ways to define the GSpin groups. The easiest way is that this is a connected reductive group whose R groups is similitude symplectic group. Okay. So this is a little bit different from the classical group case, because in the classical group case, the L groups, which can be considered kind of very roughly kind of dual groups in terms of the root system. The L groups of this one, all L groups of all these groups are also classical groups, like SO2n or SP2n or SO2n plus 1 and blah blah blah. But in this case, the GSpin groups is not a classical groups. We don't have any like a product that we can define this one. And also L group is not a classical group. It is the similitude classical group, GSP2n. So this is a little bit, this is the one different part than the classical groups. Okay. Then what we did is that the theorem, at least I need to write down our theorem. So what is that? So we classify the all isomorphism classes of discretes of Gn in terms of certain triple that I'm going to write down here. So certain triple is so-called also admissible triple. By the way, this admissible is different from the admissible representations. Just triple that satisfies certain conditions. And using this data, we classify certain discretes. So we have here, for example, say sigma. Sigma for given discretes, we to classify this one, what we need to use is induced representations that this representation embed. So what we need is like, because sigma, to explain this one, we need like induced representations where inside the parentheses, this we need to have like a representations of left subgroup. But in the case of GSpin, the left subgroup looks like bunch of GLN. And another GSpin groups of the same type. So it could be like Gn prime plus 1. So we have bunch of representations. And in the GL part, and you have GSpin part, all of these are discrete representations, which is okay because it's a discrete representation of GLN that we know. But GSpin groups, we want to classify this one in terms of the supercubital representations of GSpin 2n prime plus 1. So we need to use the supercubital representations here as C. This is supercubital. Okay. So we need all these data to classify this one. So we need the triples here. The first one is the Jordan set, which is like a pair, rho and A. Rho means representations of supercubital representations that which are the data of this discrete series. But other than the supercuspidal, we need certain the half integer data. So we need also certain half integer here, A. That will give you like a bunch of like a discrete series representations using this one. And also, of course, this is a GL part. And also, we also need like a supercuspidal representation of GSpin. So we also need like sigma SC. And there's one difference between the classical and GSpin and the general linear groups. Because in the case of GSpin groups or in the case of classical groups, these induced representations might not have the unique irreducible sub-representations. Here there's a bunch of like irreducible sub-representations. So we need to determine which one corresponds to which one. So that is determine certain epsilon function. This is the function from Jordan set, the pair that determines GL part, or pair of Jordan set 2 plus minus 1. Okay. So that will give you the discrete series representations, and then this classification is by induction, meaning that all the way down here we have the certain triple, which is called alternating triple. Meaning that the epsilon value is alternating. And this corresponds to strongly positive discrete series representations. But this is the classification of strongly positive is the first step that I'm going to skip. Okay? From strongly positive to admissible representations, by adding the pair of this Jordan set, we can fully classify the sigma. So for example, one step below this one is given by like Jordan set 1, which is given by original Jordan set, and we subtract certain pair of the Jordan set element in the Jordan set, rho and A minus. A minus means A and A minus are consecutive the integer. Okay? And also sigma SC are same, and epsilon are different because we remove the one pair of the Jordan set. So this is just restriction of epsilon to Jordan 1 set. Anyhow, by following these steps, we can fully classify the discrete series representations starting from the strongly positive discrete series representations by adding the pair of the Jordan set element in the Jordan set. Okay, then I will stop here.